Today we're going to talk a little bit about binary numbers and how computers handle them. This is a continuation of the lecture we started in class today. Why binary? It's the reason we talk about it is because this is the way computers, most modern digital computers work. Like we talked about in class, voltage levels are assigned either a high voltage or a low voltage level in the computer chips, and these are represented as either a bit of value 1 or 0. So everything that the computer handles is in terms of these 0 and 1 bits. A bit can be either of those two values, 0 considered off, 1 on. So 1 is often thought of as true, and um, and the 0 is considered false. The computers also work using binary arithmetic. So when they do their calculations, they do the adding and summing, etc., with binary values. We're not as concerned about that. We're more concerned about the sizes of things that can be stored using a varying number of bits. This will come in very handy when we begin talking about the types of data structures and variables and storage locations that are used in modern programming languages. So for example, why would you choose to store something as an int versus a long int or a short int? These are all based around how much data is being used, how many bits, and then what sizes or number of different types of things can be stored in that size number. So let's see a little bit about how these things work. So we typically say that 1 byte is 8 bits. That means I have enough spaces for 8 different numbers. So I could have slots for up to 8 individual digits in my number. Those 8 digits, each digit can only be a 0 or 1. As a result, unlike decimal, where the decimal system, decimal numbers can be from 0 to 9. So in each digit in that decimal system can carry 10 items. After the 10th item, you then carry over to the next column. So in binary, we can only have either 0 or 1, and when we exceed that in each column, we have to continue to the next column, next setting. So in this case, if I had the binary number 1010, this is equivalent to the decimal number of 10. It's probably not a very good example to use because it looks exactly the same. Let's go back and use 1011, and that would be the digital number 11. And I'll show you how that works. Come over to, I made a little spreadsheet here. Each of these columns in my binary numbers, so this white line here is my binary number. So for example, if I had the binary number 0001, that would be equivalent to the decimal number 1, because the first place in a binary number is the value 1. The second column in the binary number is the twos column. The third is the fourths, the fourth is the eighths, etc., all the way on up. You'll notice that each column is a factor of the power of 2, because binary is a base 2 number system. So each number is 2 times the previous. Just like in a decimal system, decimal is a base 10 system, so each column is 10 times the previous column. What we do to calculate a decimal equivalent is we multiply down and add across. So if I add in a 1 here, I'm adding in 1/16. So I'll have a total of 16 plus 1, or 17. And so this little trick of a spreadsheet like this can really help you write out the binary numbers that you like and see how big the numbers can be. Here, in this representation, I have represented the number 1489, which is our decimal number, is the number 101110100001. You can see that the binary system is not exactly efficient in its representation, but the computers are more than capable of handling these numbers. So we can also use this to see how big our numbers can be. If we put in all ones across here, we can see that with this number of bits, so currently I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if I used 11 bits, I can store a number up to 2047. If we include the 0, that's 2048 possible combinations. So you'll notice that that's the next power up in my table. So if I was to put a 1 here, I could store up to 4096 numbers, or this number minus 1 as my final digit. So this should be 4095 if I put a 1 in here. You'll see how this works. So this currently is a 16-bit digit number. So if I put in 16 bits, you can see how big of a number 16 bits will allow me to store. It allows me to store a number of 65,535, or I have a total number of 65,536 possible different numbers stored with 16 bits. We can do this same calculation over again with 32 bits or 64 bits. So what is this significance for us? Well, when we want to store numbers in a digital computer, we have to decide how many bits we're going to use. The more bits we use, once they go beyond the number of bits the processor can handle simultaneously, calculations get slower. So if we want to calculate numbers with very large numbers of digits in them, we have to combine together a large number of bits, and the software, the code that has to run to do those calculations becomes more complicated and therefore is slower. So faster calculations can be done with smaller bits. This is not 100% true in the sense that any bit numbers up to the size of the bits that are handled by your particular processor generally run about the same speed. So, but when we start to talk about variables and defining variables in a programming language, these come with bit sizes associated with them. Typically, in most modern programming languages, an integer is the size of a 16-bit number. It can store these numbers from up to 65,000. So the trick then becomes, how do you assign or how do you represent a negative number? In other words, I want to represent, not only do I want to represent the number, let's say I wanted to do 17. How would I represent negative 17? Well, if we go back to our spreadsheet here, you'll notice that there's no way every single thing I did was representing positive numbers. So what you do in most programming languages, take this very top end bit, and instead of defining it as 32,768 here, they define this as -1. Now, when this number is represented, it will carry the minus sign. So I'm going to modify my equation here a little bit, and I'm going to multiply by A5. So you can see that when the negative bit is on, it turns this thing negative. So for example, let me clear out these numbers, and I'll show you a different number. Let's do the number 1011. Okay, had to adjust my formula there a little bit. So you'll see that 1101 is decimal 13. If I wanted to make that a negative, I would put in a 1 in this column. So internal to the computer, the 16-bit number now becomes a 15-bit number with the 16th bit being used to represent positive and negative. So this entire number is actually filled with zeros all the way across here. So that would be the number. 10000001101 is the number represented in most computer languages as negative 13. So that means instead of having from 0 to 665,535 values, it generally goes from negative half of this. So there, instead of using a formula, I just went ahead and put in all ones, and you can see that this case, I could go from negative 32,765 up to positive 32,765 by changing whether or not this is a 0 or a 1. So if I go back to 0 here, I should now get a positive 32,767. So we can see that by storing positive and negative numbers, it cuts our total value of numbers that can be stored in half. So in computer programs, integers are stored with just straight bits. So if you need to store a number, you just have to pick enough bits in order to allow for the largest number that you're going to possibly store. So if you're storing numbers less than 32,000, you can just use a regular 16-bit signed integer. If you need to store numbers bigger than that, if you're trying to individually track the total number of people in the United States or something, we're going to assign them ID numbers and things like that. You have 300 million. You need more bits than a 16-bit integer. You might use a 32 or a 64-bit integer. Now, other types of numbers have to be stored in different ways. There's lots of ways that they're encoded, and we'll cover those in a different detail.